In this video, I'd like to talk about the perspective that sieves give on sheafification. So using sieves, or using some reasoning which is made possible through sieves, we'll be able to come up with a new description of the sheafification functor. Now, I'm not actually going to prove anything in this video because I don't know of any nice proofs that say this construction actually works and is actually sheafification that actually lives up to its name, but I do think that it's something worth knowing about. So I want to present the construction even though I'm not going to prove that it actually is sheafification. Okay, so what's the project of sheafification? What are we trying to do? So what we want to do, in general, is, well, we start out with this category of pre-sheaves on a topological space X, and we want to come up with a map, a functor, into the category of sheaves on X. So maybe we'll call this functor sigma. So we want to come up with a functor from the category of pre-sheaves into the category of sheaves. And we would like this functor to be the adjoint to the inclusion from pre-sheaves, or sorry, from sheaves into pre-sheaves. So we'll call this guy inclusion, and we would like this to be is the, I believe it should be the left adjoint. Yes, we want sheafification to be the left adjoint of inclusion. So that's the project of constructing a sheafification functor. It's sort of coming up with some actual semi-concrete way of realizing what this adjoint is. I mean, adjoints are unique up to isomorphism, so I guess we could define sheafification. We could define sheafification to be the left adjoint of this inclusion. But you could wonder whether this actually exists. So in practice, people like having ways of actually constructing this functor. So in the étal series, I gave one way of constructing it, and now we're going to talk about another way of constructing it. So the way that we'll construct it is kind of with two repetitions of a single step. So we'll start out with this functor from O of x to O of x hat, and this functor, I'm just going to write down a name for it. This is meaningless at this point. This functor is going to be the functor that maps f to something called f plus. So I guess we could write this as just plus. It's plus with some variable here. And what we'll do is apply this functor twice. So then we'll apply this functor f maps to f plus again. Here I'm just outlining what I'm going to do in this video. We're going to define this thing plus, and I'm just trying to tell you what the setup is, what this thing plus is going to look like, or what diagram it kind of fits into. I'm just trying to outline the program of this video quickly. So we'll define this plus operation. Write it again down here. And it will happen that f plus plus is always a sheaf. So for any f inside of O of x hat, it'll be the case that f plus plus is a sheaf. And by that I mean you take f, you apply the plus operation to it once, and then you apply the plus operation to it again, and you'll get a sheaf. And it's going to turn out that the functor taking f to f plus plus, that's sheafification. So that functor, the functor that takes f to f plus plus, that functor which goes from here into the category of sheaves, that'll actually be the left adjoint of inclusion. So it'll be sheafification. Now again, I'm not actually going to prove that. I would just like to tell you what this plus construction is. That's the only purpose of this video formally, is to tell you what this plus construction is. I'm not actually going to prove that f double plus is sheafification. But I think the construction is worth knowing. Okay, so to describe the construction, we need to first recall what it means in Sieve world to be a sheaf. So we have a topological space X, and we have some pre-sheaf f on X, and f is a sheaf if and only if this condition is satisfied. If and only if for every open set U of X, and for every covering sieve S on U, this map, the induced map on Hom sets, and these Hom sets are living in O of x hat, maybe I'll point that out, is an isomorphism. So one way of saying this is that maps from H of U into F are equivalent to maps from S into F for any covering sieve S. So H of U and S kind of act the same with respect to mappings into sheaves. Okay, so this is what the definition of a sheaf is in the sieve world, and we would like to use this definition to kind of figure out what the plus construction should be. So the first step there is thinking about what this guy looks like. Sort of another way of writing this. So by Oneta, this Hom set is something maybe a little bit more concrete. By Oneta, it's the case that Hom in O of x hat from H of U to F is isomorphic to F of U. So really, and here's the punchline, so really, F is a sheaf if and only if the map from F of U into Hom O of x hat SF is an isomorphism for every covering sieve. For every covering sieve S on U. And this map here, that's just you apply Oneta first, and then you apply this restriction map that we had over here, this functional restriction map. Okay, so that's the first thing we should note. And now the second thing we should note is that we can kind of collate all of this data into a single condition. So, in order to apply this definition as exists to check whether F is a sheaf, we kind of have a lot of individual conditions, right? For every covering sieve S, we have this individual condition. For every covering sieve S, we have this condition that this map is an isomorphism. So what we'd really like to do is get rid of that huge collection of local conditions by collating them into one very complicated single condition. And we were really just going to be cheating because we're just going to kind of glue all of these conditions on all these sieves into a single condition. But let me just say what that condition is going to be. So this is the second step. So we notice F is a sheaf if for every, I guess I still have to say for every U inside of O of X, the map from F of U into the direct limit, this time, of all covering sieves S on U of Hom from S into F is an isomorphism. Okay, so let me back up for a minute and sort of say where this thing comes from. Maybe I'll post a detailed video doing this more formally, but let me just say intuitively where this comes from, which is that, well, from this reasoning, right, we started out with this definition, then we applied Oneta, and we said we have this map from F of U into Hom from S into F, and we have this map for every covering sieve S on U. And we don't want to have to kind of apply this condition to every covering sieve S on U. We'd like to kind of bundle all those sieves into, all those conditions into a single condition. And when we bundle all of those conditions into a single condition, we get this condition. We get this condition on this direct limit. So let me briefly say what this direct limit is, just to clarify here. So one way of thinking of this is that we're going to take the direct sum over all covering sieves S of the Hom from S into F, and we're going to quotient by some relation. And the relation is going to be that, well, given I guess, given a map from S into F, which we'll call F, and given a map, maybe S prime, into F, which we'll call F prime, so given something like this, we write F is equivalent to F prime if there is some smaller covering sieve, maybe T, smaller covering sieve T on U, such that this diagram commutes, such that T being included into here, and then included into here, such that the above diagram commutes. So I think the cute way of saying this is that you take all of the maps, right, and you quotient out if they restrict to the same thing on some smaller sieve. So you take all maps from all covering sieves, you take that direct sum, and then you quotient out by saying that two maps are equal if they become equal on some restriction to some smaller covering sieve. And this is something which happens a lot with direct products, right, with like germs of functions or with tangent vectors, or one definition of tangent vectors, for example. You sort of identify functions if they become equal on some smaller domain. So that's all we're doing here, and that's what this direct limit looks like. Okay, so we've explained what this direct limit is. Maybe I should quickly explain what this map is. I mean, this map is just the natural thing. We have this map from f of u into hom from h of u into f. That's just by Yoneda. And then by this restriction, we have a map from hom h of u f into hom from s into f. And you kind of collate all of those maps together to get a map into this direct limit. Or you project all of those maps together to get this map into the direct limit, whichever you prefer. Okay, so remember the whole point of doing this was that we didn't want to have to check this definition for every individual covering sieve. We kind of wanted to take all of those conditions on individual covering sieves and put them into a single condition. And that's what we did here. So we now know that f is a sheaf if and only if for all u inside of x this condition holds. And this condition just depends upon u now, right? Because we've kind of bundled all the covering sieves together. And that's what we wanted. We didn't want to have to look at the individual covering sieves. And now, at least semi-formally, we don't, because we've kind of hidden all of that data under the rug of this direct limit. Okay. So this is so important, I'm going to write it again and then make a comment on it. So, f inside of O of x hat is a sheaf if and only if for every u inside of O of x, the map from f of u into the direct limit over all covering sieves S on U from hom S F is an isomorphism. And this is the point that we've been leading up to. So this remark, this so here, is kind of the result we've been trying to get to by all that prior discussion. This is really the condition that we want to start with. Okay, so we know that this is true now, right? We know that the sheaf condition can be expressed by saying that f of u is isomorphic to this direct limit. And in general, because there are pre-sheaves which aren't sheaves, this might not happen, right? This might not be an isomorphism in general. So how can we sheafify f, right? If we have some f for which this isn't an isomorphism, what do we do? Well, let's just be hopeful by defining some new thing, which we'll call f plus of u, and we'll just make it by fiat be equal to this limit over covering sieves s of the hom s f. So maybe for our original thing f, we didn't have this isomorphism, but we'll just define f plus so that we kind of have this automatically. So automatically f plus of u is just equal to this thing over here. Okay. Now we can wonder now, is f plus a sheaf? So for that, what we really are wondering is just because of this condition, is it true that f plus of u is isomorphic to the limit overall covering sieves s on u of hom s f plus? So this plus is really a sort of what makes all the difference in the world between this comment and this comment, right? The way that we got f plus from f was to look at f and say, well, look, f might be deficient somehow and that it's not isomorphic to this thing. We'd like f of u to be isomorphic to this direct limit, but it's not. So let's try to make f better by making this new functor f plus, and by fiat we'll just set f plus of u to be equal to this direct limit. But this doesn't guarantee that f plus is a sheaf, right? I mean, f plus was defined with this condition on f, but the sheaf condition, this condition, is on f plus. So asking whether f plus is a sheaf is asking whether f plus satisfies this isomorphism, not this one, which it trivially satisfies. And the answer, sadly, is that not always. So sadly, this doesn't always happen. So it might be the case that f plus of u is not isomorphic to this thing. Okay, well, maybe we're not ready to give up yet, and we just say, well, let's try again. Let's try again. So just to narrate here, we started with f, and f turned out to be deficient because this isomorphism didn't get satisfied. So we moved to f plus in an effort to kind of fix that deficiency by making f plus of u be what we wanted f to be by definition. And now we're saying that f plus might also be deficient, right? It might again be the case that f plus of u is not equal to this direct limit. But let's just try again. I'll just apply the plus construction again. So we'll go to f plus plus of u. And by definition, this is equal to the limit overall covering sieves s of hom s f plus. So we're again going to try to fix that deficiency. And this time, here's the small miracle, this time it works. Sort of there's no more completion to do. So by works, I mean f plus plus is a sheaf. That is, so f plus plus of u is actually isomorphic to limit overall covering sieves s on u hom s f plus plus. So even when we defined f plus plus over here, we only had one plus on this side. It turns out we actually get everything. And this is a non-trivial fact. So I'm not going to prove this because I don't know of any proof that isn't painful. But maybe if I eventually find one, I'll put it up as a detail video. Let me just say that for the masochists out there, even though I'm not proving this, you can find a proof. And you can find it in the book by McLean and Mordyke, for example, the Sheaves in Geometry and Logic. And of course, all of this stuff is in SGA. I think this is an SGA 4 Expose 2. Okay. So let me briefly recap and then we'll be done. So the recap is that we defined this functor from O of x into O of x, and that was the plus construction. And I claimed that sort of f maps to f plus plus, that functor, is sheafification. I didn't prove this, But I do think that it's something kind of worth knowing.